Last time we started section 1.2, and we're looking at patterns, is what we're looking at in this section. We had talked about some different kinds of patterns, arithmetic and geometric being the two biggest things we talked about. But we also looked at Fibonacci sequences, and I talked about first and second differences a little bit. And we're going to take a look next at an item called figure numbers. So figure numbers are based on visually geometric patterns. These examples are neither arithmetic nor geometric. Such numbers can be represented by dots arranged in the shape of certain geometric figures. And the one that we're going to start with are triangular numbers. All right, so I'm going to develop the triangular number shape or the numbers of them by the shape. So the first one actually, it mentions dots, has one dot. The second one in the pattern has three dots, and they're in the shape of a triangle, hence triangular numbers. And then the next one looks like this. And then we have four dots along the bottom, like this, and the pattern would continue. So there's a visual motivation. You can describe this in several different ways, even from a visual perspective. You could talk about like, oh, it looks like you're just adding another row on the bottom that's one bigger, right? That's sort of how my brain sees it. But it doesn't have to be on the bottom. It can be on the right-hand side or the left-hand side, and you still have the same image. So what we're wanting to do, though, is to look at what happens with the numbers that are associated with the number of dots, like when we count the dots, how many there are. So we're going to list them out. So the first one is one dot, obviously. Actually, let me write it over here to the side so I can play with the numbers here in a minute. One dot. How about the second one? 3. And then 6, and then 11. Is 11? I think it's 10. Is it 10? Yeah, 10. Okay. So take a look real quick. It's not geometric because if I tried to multiply, 1 times 3 is 3, but 3 times 3 is not 6, right? So it's not geometric. It's also not arithmetic. 1 plus 2 is 3, but 3 plus 2 is not 6. So it doesn't follow either of those patterns. But it is a pattern I showed you last time, so I'm going to actually draw out what happens when we look at the addition a little bit further. This is addition of 2. 3 to 6 is addition of 3. 6 to 10 is addition of 4. We saw this last time, right? And if we did it again, like if we looked at the pattern between these guys, they're all in common 1. So they have what's called a common second difference, right? And the shape that they're creating is triangular, so we call them triangular numbers. Okay, you ready for another one? So the next one is called square numbers. So square numbers are going to be in the shape of a square. Yeah. So the first one is a single dot, just like before. And then we start with dots in the shape of a square. So this is a 2 by 2 square, and then we have a 3 by 3 square. I'm going to do one more. Okay, it's kind of losing its squareness the more I go because the drawing is worse. As you can imagine, it's supposed to be square, right? And the pattern continues. This one has a couple of different ways you can recognize the pattern. So let's write down the numbers here first. This is a 1. Actually, I'll write it to the side the same way I did. I have more space in the bottom. I'll write it underneath here. So I have a 1. And then what do I have? I have a 4, right? How much is the next one? 9. They're 9. 16. Okay, so one way to recognize these is that what do we call these numbers from a high school, I see these numbers kind of standpoint? Like what are these called? They're the squares, right? These are the square numbers, right? So if you were to write them out, this is 1 squared and 2 squared and 3 squared. My squares aren't looking so good. And then 4 squared. They're the powers of 2, right? So the next one would be 5 squared, and we'd have 25, and then we'd have 6 squared, and it'd be 26. So that's one way to recognize this pattern. Okay, it's not the only way. If I looked at the one for 9 and 16, those are the ones I'd written already, we could actually do the same thing we did in the last problem. How do you get from 1 to 4? Add 3. 4 to 9? 9 to 16? And if we did it one more time, they're adding 2 each time. It's a common second difference, just like the last pattern. But it has yet this other squaring way of writing things in, right, as well. So there's more than one way to recognize that particular pattern, and these are square numbers. All right, any questions on that? Okay, last example in this section before we shift to the next, to 1.3. This is something that happened in real life. Where were you in 2011? It's a long time ago. On a playground, probably. Yeah, probably so. It's not even called this anymore. This is what happens when you're at an institution and they keep changing things in an institution. So the math division that I'm in now used to be called the Department of Mathematics. We used to be inside of the Hurley College of Science and Math. We're now the Hurley School of Science and Math, and things keep changing. But this was the inception of the Hurley College of Science and Math, and our dean at that time wrote something on the board. She wrote down this on the board, okay? And she asked us to find the next 2 things in the dot dot. So I want you to do that right now. If I give you this, I would like for you to figure out what you think the next 2 numbers should be in this list of numbers. Okay? Audience participation time. Just write it down. We're going to talk about it, I promise. Okay, so there's usually 2 different things that people say here. So there's 2 distinctly different answers I get the most. So somebody tell me what you wrote down. What'd you get, Faith? 92. How many wrote down 92? Okay, so 3 of you did because Faith gave her answer. What else did you guys write down? 1-6. How many of you wrote down 1-6? Okay, so you're not, neither one of you are right or wrong, okay? So this is what was written, if you had it. So this is what almost everybody in the room wrote down when we did this. Any idea? Actually, we're going to pick on Faith because she's the one who answered for me first. Why did your brain go to that? It's pi. It's an expansion for pi. Who was this given to at the time? Math and science people. So does it make sense that the math and science people looked at 3.1415 and said, well, obviously, and they wrote down 9-2. Those of you who wrote down the 1-6, somebody tell me why 1-6? Right, it goes 1-4-1-5, and so your brain went to a different kind of pattern, yeah? Neither one's right or wrong, but it's one of those things that shows you, down at the bottom, about inductive reasoning, is that inductive reasoning doesn't always work. Right? Inductive reasoning is where we look at a pattern and we make a generalization, then we say it's going to do this next. And we have 2 possible answers. Neither one's wrong, but they're definitely different. Correct? There is an example in one of the lists of numbers that you get where it asks you to try and come, I think it says something like to try and come up with a couple of different ways that the pattern can be continued. And it depends on how you see it as to which ones, you're probably going to find one, you're going to be like, well, this one's obviously it. It's probably going to take you a minute to try and figure out what the other one it could be because your brain didn't go there first. So inductive reasoning sometimes falls short. That's what it's supposed to say on the bottom. Are you good with that? All right.